Let's talk about deep learning. Deep learning is a subset of machine learning, and while machine learning is inspired by the way humans learn, deep learning is inspired by the way our brains work. Our brain transfers information to and fro between nerve cells called neurons, and these neurons process and transmit information, and we have over 80 billion of them in our brain. And this was the inspiration for the technique that we now call deep learning. And deep learning uses something called artificial neural networks. And this is what a deep learning artificial neural network looks like. This is a very simplified example, but essentially there are three parts to a deep learning neural network. First, there is an input layer where the raw data is input, and then there are the hidden layers, and these are the layers where the analysis is done. And neural networks are feed forward in that information flows in one direction from the input layer through the hidden layers where the analysis is performed, and the result of each analysis is passed from one hidden layer to the next hidden layer until it reaches the output layer where the final output is processed. And the network is comprised of nodes, and each of these nodes are called a neuron, and that is where the data is being processed, and the connections between the layers are called channels. And the hidden layer component is where the actual brains lie, and this can be as small as 2 layers to hundreds of hidden layers. And broadly speaking, the deeper the neural network is, that is, the more layers it has, the better it is likely to perform. However, with more layers comes greater complexity and the greater need for training data. If you have only a couple of layers, the training data required would be significantly less than if you have, say, 22 layers. So how do neural networks work? Well, let's take a look at an example to try to understand this. Let's imagine that we're trying to build a model that is able to differentiate between a square, a circle, and a triangle. So here's an image of a circle. Let's say it's composed of 28 by 28 pixels, and altogether this makes up 784 pixels. So in this case, this is an image recognition challenge, and so we can feed these pixels directly in as inputs. So we would have our first layer comprising of 784 nodes or neurons. And then we would also have an output layer, which would be the final result. And we would have 3 nodes here, one for a square, one for a circle, and one for a triangle. And in between would be the hidden layers, which perform most of the computations that are required by our model. So once the 784 pixels are fed in to each neuron of the first layer, these neurons are connected to the next layer through channels, and each of these channels is assigned a numerical value known as a weight, and then the inputs are multiplied to the corresponding weights, and their sum is sent as an input to the neuron in the next hidden layer. And each of these neurons are associated with a numerical value called the bias, which is then added to the input sum. And that brings us to 2 important concepts that we need to cover, which we've covered previously in linear regression, and that is weight and bias. So the role of weight and bias in a neural network is very similar to that in linear regression. Weight determines the extent to which that particular variable influences your outcome. So if I'm trying to predict rainfall, then perhaps the presence of clouds would have a greater weighting than something else, such as the current temperature. And in the linear regression example, we saw that weight is associated with the steepness of the line, and bias determines the placement of the line. So in this linear regression example, coefficient 0 is your bias and coefficient 1 is your weight. And with the neural network, you can think of weight as increasing the steepness of the activation function. And this means that weight decides how fast the activation function will trigger, whereas bias can be used to delay the triggering of the activation function. So what exactly is an activation function? Well, you can think of the activation of a node in a neural network as the lighting up of a node. If you've seen any animations of neurons in the brain and how they work, oftentimes they depict them by showing them lighting up, and then the corresponding neuron lights up next to it, and oftentimes that's triggered by some kind of input signal that is moving along and lighting things up as it moves along its journey. Well, this is essentially inputs that are triggering the activation of neurons, which in turn are then triggering activations of other neurons downstream. So the lighting up of those neurons is what we mean by activation, and the activation function defines the rules that determine when a neuron should be lit up. So the input value, the bias, and the weight determine, along with the activation function, whether a neuron is activated, and an activated neuron transmits data to the neurons of the next layer, and in this manner the data is propagated through the network, and this is called forward propagation. And in the output layer, the neuron with the highest value will fire and determine the output, and these values within the neurons are basically a probability. So in this example, we have arrived at an output that predicts that this image is a square with a 50% confidence. And as you can see, the model got it wrong, and that's because it hasn't been trained yet. And the way that neural networks are trained is that initially the weights and biases are set at random values, and then the output of the model is then compared with the actual correct output. The nature and the magnitude of the error is examined, and then this information is then transferred back through our network, and this is known as back propagation. And now, based on this information that we've learned, the weights may be adjusted, the bias may be changed, and even the activation function may be updated. And then we go through another cycle of forward propagation to see if we arrive at better results. And this whole process is then repeated until we arrive at a model that is able to make a prediction at a degree of accuracy that we're comfortable with. So that is a quick primer on deep learning. This is one of the more complicated approaches to machine learning. In a future lesson, we will also examine when to use approaches like deep learning. But we're done for now, so I will see you in the next lesson. Bye-bye.